Hi guys, this is Dr. G here, and in this video we are going to talk about hydration of alkenes or addition of water to alkenes. And before this video I have also published videos on the general introduction to alkenes, nomenclature of alkenes, and also electrophilic addition to alkenes, and most importantly synthesis of alkenes and the halog- uh, halogenation of alkenes and halohydrine formation of alkenes. So those are some of the videos that I highly recommend you to study, because those videos may have some important things for this particular video. So basically hydration of alkenes or addition of water into alkenes can be done in three different ways. And of course uh, the first method that I'm going to discuss for the hydration of alkenes involves water for hydration, of course, and then a strong acid catalyst. The typical strong acid catalyst that we usually use is phosphoric acid. So you can use phosphoric acid as the catalyst, and you might need a little bit high temperatures for this reaction. So this reaction is going to be a Markovnikov addition, which means of course the rich carbon gets the hydrogen and the poor carbon gets the OH. Okay, so basically hydrogen is gone to the rich carbon, and then OH is gone to the poor carbon. Okay, so as an example, let me talk about a general example like this one. Let's take propene as an example. It is a very simple alkene, propene. Okay, so for propene you have two asymmetric sp2 hybridized carbons. Okay, which means this carbon right here is considered rich, this carbon in the middle is considered poor. Okay, why? Because the carbon right here, the rich carbon, has two hydrogens. Hydrogen is like money, so if you have more money you are rich, right? So the middle carbon has only one hydrogen, so it is poor. Okay, and then if you that is how you basically identify rich and poor carbons. And if you try to hydrate this alkene using using water and of course phosphoric acid at high temperatures, what you get is something like this. You started with propene, but of course you are getting rid of the double bond. Excuse me. You're getting rid of the double bond. So let me erase the double bond right here. And then the poor carbon gets the OH, the rich carbon gets the hydrogen. Okay, so that is how it happens, and this is according to Markovnikov rule. Rich gets richer. Okay, rich gets richer, so therefore hydrogen the carbon with more hydrogens get one more hydrogen. Okay, all right, so we already discussed about Markovnikov rule before. So here's the mechanism for this hydration, and this is basically the general electrophilic addition mechanism. So okay, so you are going to have a carbocation. Okay, you're going to see a carbocation in this mechanism, and then of course carbocation is open, which means the incoming water molecule in the second step can attack from the top or bottom and then give you an OH. Okay, so the rich carbon gets the hydrogen, poor carbon gets the OH. Okay, typical electrophilic addition reaction. Typical electrophilic addition reaction. And in here I have an example for acid catalyzed hydration in biological pathways, but for this reaction we are not going to worry too much about biological pathways, but if you are interested you can take a look at it, and I highly recommend that you read the textbook if you want to get some more details on acid catalyzed hydration in biological pathways. And then we are going to talk about the next hydration reaction, which is the second one we are going to talk about in this video. And the name of this hydration is called oxymercuration, deoxymercuration procedure. This is actually a very common procedure or reaction done in the laboratory to hydrate alkenes. This reaction is very simple. Okay, you need a couple of different reagents. Okay, for the first step you are going to need mercuric acetate. Okay, and water. That is your first reagent. And in the second step you are going to need sodium borohydride. I recommend that you guys add this reaction to your reaction book, because this reaction is going to be extremely important in your organic synthesis type problems. Okay, and then the important things about this reaction is that this is this behaves according to Markovnikov addition. So this resembles the phosphoric acid based hydration reaction. And also the other important thing is that this is an the products are or they tend to look like trans, or in other words, the hydrogen and the OH group are going to be on opposite planes if you have a cyclic product. So those are the two things that we have to worry about: the Markovnikov addition and the anti-stereochemistry. So the other important thing about is that we saw anti-stereochemistry before during the halohydrine formation. So during that halohydrine formation, what we saw was that the formation of a bromonium ion, basically prevented the incoming nucleophile. So therefore the nucleophile could only reach from one end, from the opposite end to the bromonium ion. So that is why we saw anti-stereochemistry. And here we can still see that this mercuric acetate basically forms a cation which we call mercurinium ion, which is very similar to bromonium ion, and it basically blocks one side, or it basically shields one side of the ring, so that the incoming water molecule can only come from the opposite plane, so that is something important that you have to remember. So that is why this reaction behaves as an anti-stereochemistry. So if that is the case, the actual product that you get should have the OH group, let's say, on the dash, on the wedge, and then the hydrogen should be on the wedge. Okay, so that is how you show anti-stereochemistry. All right, so let's see if you could do this worked example. If you are watching the video, you might want to pause the video now and then see if you could do this by yourself. All right, so in this worked example, the two compounds that we have are not cyclic, which means we do not actually have to worry about the anti-stereochemistry. The only thing that we have to worry about is the Markovnikov's rule, okay, which means we have to figure out the rich carbon and the poor carbon for these two starting materials. And then the poor carbon gets the OH. Okay, so fourth carbon, 1 2 3 4, fourth carbon gets the OH, and the fifth carbon, the last carbon get the hydrogen. So in this one, the second carbon gets the OH, the third carbon gets the hydrogen, so it will be a CH2, CH2, CH3. So these are the two products that we will obtain from this reaction. So let's see the solution. I mean, this is basically the same thing that I just mentioned, but if you want to spend more time on this solution, you can pause the video and then see if you understand the whole thing. All right, but once again, I want you to pay attention to the reagents. Okay, so these reagents are added in two steps. In the first step, you're adding the mercuric acetate and water, and in the second step, you're adding sodium borohydride. So let's summarize the significance of oxymercuration reaction. It behaves according to Markovnikov rule, and if you have a cyclic alkene, the addition could be anti-stereo. The addition reaction could be anti, okay, which means you are getting a trans kind of product for the hydrogen, for the incoming hydrogen and the OH. Third and final type of hydration that we are going to talk about is called hydroboration. It's called hydroboration. By the way, there's a typo here. Let me fix it really quickly. Okay. All right. So the final hydration reaction that we are going to talk about is called hydroboration. And hydroboration is actually, you could say, directly opposite to oxymercuration. It could be directly opposite to oxymercuration. Why? Because hydroboration is non-Markovnikov, which means hydrogen is not going to go to the rich carbon. Instead, it is going to go to the poor carbon. So this is non-Markovnikov or anti-Markovnikov. And also, oxymercuration was anti, and hydroboration has a syn stereochemistry. Okay, so that is also opposite to oxymercuration. That is also opposite to oxymercuration. So here is an example. Let's use the same example that you have on your lecture note. Okay, so basically here is your rich carbon right here, because it has one hydrogen, and this is your poor carbon. Okay, rich and poor. This is not very clear. Let me just use the pen. Okay, so this is your rich carbon. Here is your poor carbon. Okay, and hydroboration is non-Markovnikov, so the rich carbon should get the OH. See, the rich carbon got the OH, and the poor carbon got the hydrogen. So this is non-Markovnikov, or you can say anti-Markovnikov. And this is the most important thing, or the most important difference between oxymercuration and hydroboration. And if this is also another example for hydroboration, and in fact this one is very straightforward, to be honest, because even though you have a cycle, you don't have to worry about anti or syn stereochemistry. Why? Because the two carbons of this alkene has no substituents, so you don't have to worry about anything. Just give the OH group to one carbon and the hydrogen to the other, and that's it. But if you have an alkene, a cyclic alkene like this with a substituent, then clearly you have a rich carbon and a poor carbon, which means you can worry about the Markovnikov addition or anti-Markovnikov addition in here. And then also you will have to worry about this syn and anti-addition. You will also worry about syn and anti-addition. And in here, of course, the poor carbon gets the hydrogen. So hydrogen went to the poor carbon and the OH went to the rich carbon. That is not the only thing. This is actually syn addition, as I mentioned earlier, which means both hydrogen and OH are on the same side of the ring. That is why, I mean, in your textbook, they are using a dash bond to denote that both hydrogen and OH are on the same plane. So that is an important thing to remember. So here is the mechanism, or this basically explains the final product using the intermediate. Okay, so as you can see, in BH3 the electrophilic atom is actually boron. So boron is going to align with the rich carbon, But the thing is, the BH2, the resulted BH2 is converted to the OH group. So even though you are getting the electrophile boron atom aligned with the rich carbon, it is then converted to the OH. So therefore, it is going to be anti-Markovnikov. The other thing that I want you to worry about is the reagents. So for the hydroboration, in the first step, you can add BH3. And in the second step, you will add hydrogen peroxide in basic medium. So these are the reagents for this reaction. All right. Once again, this is anti-Markovnikov and syn addition. Keeping all these things in mind, let's see if you could do this worked example. If you are watching the video, you might want to pause and then work on this problem. All right, so in this worked example, they're asking us to come up with the alkene that might be used to prepare the following alcohol using hydroboration. Okay, so basically in hydroboration, rich carbon gets the OH and the poor carbon gets the hydrogen. So this is very straightforward. This is the alkene that you should use. Right, this is the alkene that you should use, and these are the reagents, of course. All right. With that, I'm going to conclude this video, but I recommend that you guys watch this video multiple times, and of course come up with maybe a table to distinguish between the similarities and differences between the three techniques. Okay, with that, you guys have a wonderful day. Thank you.